So in this part, I want to talk about a very important concept which we will meet throughout the course, and it's important to establish it from the beginning. So I'm going to talk about removal rate from an equation and the expected time spent in a category. And by category, I mean the status in a model. So for example, infected, susceptible, and so on. So it's not a difficult concept, but it's probably new for most of you, and it's something that you shouldn't rush into it. Once you understand the main idea, it will be very easy because it's not actually a lot to remember. It's essentially a more detailed exposition of what we mean, why we give some interpretation to removal rates, essentially, to reciprocal of removal rates, to be more precise. So before we move on into the main idea, let's remember the exponential ODE. In the notes, we solve this in more details. At this point here, I just mentioned the main, the general solution. So if you have an ODE in which the rate of change, dy dt, is equal to some constant times y, then the general solution is just an integration constant c e to the kt. So if the rate of change is proportional to the quantity itself, the rate of change of a quantity, remember this is a constant, that's important, then the solution is in the exponential format. And more specific to population models, if P of t, let's say, denotes people at time t, and you start with some initial population size denoted by P naught, then the exponential ODE. So if you have dp dt equals some rate of change, which in its simplest meaning could be just the difference between the birth and the death rate, and like I said, P naught equals P of 0 equals P naught, then the total population value at time t will be P naught e to the RT. So in the exponential ODE, the constant of integration denotes the initial population size, if you have this condition here. And I said before that in the notes, usually R denotes the difference between the birth rate and the death rate. So often, for example, in models, you will see P prime equals some birth rate times the population size minus the death rate times the population size. So of course, you can factor P, and then the solution can be written as P naught e to the B minus mu times T. If you sketch the solution of this is nothing fancy, just the solution of the exponential ODE. You have basically two main cases. So let's say this is the initial population size. Population goes to 0 exponentially, right? If B minus mu is less than 0 or R less than 0. Population grows exponentially to infinity. If B minus mu greater than 0 or R greater than 0. So in this case, P of t goes to infinity. One of the simplest population models, but one of the, of course, the least realistic ones, because exponential growth is quickly out of realistic bounds as time goes to infinity. But the point of this part essentially is to give a meaning to 1 over mu. You will see often, and let me actually preface this a little bit, you will see often in math biology papers that even if you have more complicated expressions, the author of the paper takes big pain and time in rewriting these conditions in such a way that the death rate appears at the denominator. And it's very important to understand the reason why we do this, because if you skip this part, it's going to be basically feel like you're trying to add more work than necessary to the problem by doing this algebra. So for example, one way, and the correct way actually, in rewriting this so that mu appears at the denominator, this condition, for example, the condition that population grows, is to move mu on the right-hand side and then divide both sides by mu. So the same condition that gave me the growth of the population can be written as b over mu greater than 1. In this model, it's so simple, it's nothing too fancy to understand, right? I mean, the birth is greater than the death. Nothing too hard to understand why the population goes to infinity. If the birth is greater than the death, obviously p goes to infinity. What's the big deal that I write it in the form of b over mu greater than 1, right? Birth greater than the death in the fraction form means it's greater than 1. But why this is so more important than all other equivalent expressions? So with that in mind, if you look at the notes, I mentioned, and let's state it here, and then we're going to justify it later. I say that when you take the reciprocal of the removal rate, in this case the death rate, you basically get the expected time spent in that category. In this case, we have just a single category, the population at time t. So 1 over mu essentially is like the expected lifetime. All we have here is birth and deaths in the model. And if I take the reciprocal of the death rate, the meaning of this reciprocal death rate is that it approximates the lifetime of the individual. So there's a far more interesting or easier to understand biological interpretation of this. If 1 over mu is the expected lifetime and the birth is the birth rate per unit of time, basically this quantity, the birth per unit of time multiplied by the lifetime of the individual, this quantity, this product essentially approximates the number of offspring of the individual during his lifetime. So basically biologically, and we're going to talk about this more often in more details, biologically this one says, should an average individual during his lifetime produces more than one offsprings, then the population grows. So it's far more logical and far more intuitive to understand in terms of a condition. Now, again, not much of a difference between birth and death, but the problem is that in many data points, the expected lifetime can be computed by other means, which will give you essentially an estimation for the death rate and so on and so forth. So this quantity, 1 over the removal rate, is important because it approximates this expected time spent in that category or the lifetime of the individual. So let's move on the same part on the second page here, and just this part is given in the notes as well, but I want to briefly justify it, very briefly, because we don't want to go too deeply into the probability theory. Just take it basically as a given that 1 over the removal rate is the expected lifetime. We can get some intuition why that's the case though, and I did this on the notes, but let's do it here as well. So the solution of the population, let's say for simplicity, actually, let's do it differently. So for simplicity, let's say you have a population that is modeled just by the death. So no one is born. You only have the death rate in the population. So the solution of this ODE is the initial population e to the minus mu t. Obviously, everybody goes to 0. I mean, the p of t goes to 0 in the long run if you have only deaths. But I want you to think about in terms of the probability. Again, we don't get into details into continuous probabilities, but let's say starting from time 0 up until time t, you want to assess essentially how many people lived and how many people died. So you start with some population, p naught, and at the time t, there's p naught e to the minus mu t remaining. Okay? So if that many remaining at time t, how many had died at, in this interval? So how many deaths by time t? Well, that's the difference between the two. Initial minus remaining population. Okay, so if you want to basically assess overall the probability of dying in this interval of time, so think of this t as the age, for example, right? So I mean birth, and then by the time t, basically what will be the probability of dying in that population would be this difference divided by the total population size. So 1 minus e to the minus mu t will be basically essentially the probability that you died in this interval, in the interval 0t. So the probability of death in the interval 0t. And notice that it makes sense, starting with the beginning, the probability is essentially 0 when you measure the time, right? If you plug in, I should put here minus, sorry about that. So if you plug in 0 for t, that's going to be e to the 0, which is 1. 1 minus 1 is 0. As t goes to infinity, this exponential goes to 0, and the overall probability is 1. So as t goes to infinity, the probability of death is certain, right? I mean, it approaches 1. But in the interval 0t, then you have basically this probability. It's actually the probability distribution. There's more formality on this that I want to go into right now. But if you take this probability and you differentiate it, so let's differentiate this probability, which you get minus mu e to the minus mu t, you get what we call basically the probability density function. So think about what the derivative means in terms of the rate of change as you learn it in calculus 1. So this function up to t is the probability of dying by the time t. Imagine a nearby point t plus h. If you take the rate of change, which is given by the derivative, it's essentially the probability of dying right at that moment, at time t. So you could think of this as approximating, describing the probability of dying just at that moment at time t, whereas this one is the probability of death in a given interval. So you could think of this as the probability of living by age t. You died at age t, therefore this is the probability of that happening, that, living t years, for example. So when you compute the expected value of the random variables, remember you multiply the outcome with the probability of that outcome, and then you sum up if it's a discrete probability. In the notes, I talk about that example with rolling a die, for example, and then attaching an outcome to each probability. In the continuous case, the summation is replaced by an integral over all possible outcomes. In this case, 0 infinity, right? Because the time goes from 0 to infinity. The outcome is the age, like I said. Excuse me, not the the outcome is the ht, and the probability of that outcome is going to be mu e to the minus mu t. So we show that, I'm not going to go into this right now, we show that in the notes, this probability is actually 1 over mu. Actually, you know what, why don't you do it for completion, just in case someone sees this and doesn't have access to the notes. So this integral can be solved by parts. So let's do it by parts quickly. We can write this part as a derivative by taking, let's see, we can write mu e to the minus mu t as the derivative of minus e to the minus mu t. Okay, let's check. If we differentiate, we get minus mu again outside. It cancels with the minus, so you could write this as minus e to the minus mu t prime. Let's do it by parts. You need to go over improper integrals to fully understand this. So it's minus t e to the minus mu t between 0 and infinity, minus the interval from 0 to infinity, t prime is 1, and then minus e to the minus mu t dt. If you take the limit as t goes to infinity, this goes to 0. If you plug in 0, that's also 0. So we have 0 minus 0. Let's cancel this minus with minus. So we have plus the integral from 0 to infinity, e to the minus mu t dt. The antiderivative of this is minus 1 over mu e to the minus mu t between 0 and infinity. When we plug in infinity again, it's 0 in the limit. When we plug in 0, it's e to the 0, 1. So it's minus 1 over mu. So if, again, this is too much in terms of the proof, I want to mention clearly that for this class, you don't actually need to know this proof, but I just wanted to give you a little bit more formality on why we have this interpretation of 1 over mu in terms of the expected lifetime, right? I mean, because in this setting, essentially, this is what this measures. If mu is the death rate, you basically sum up the probability of living up to all possible ages from 0 to infinity, and then the expected value happens to be 1 over mu. In probability courses, this is essentially very well established. You'll learn this very well. Not a crash version like in this case. However, let me finish with the important part for our purposes. So from now on, always remember this interpretation of this 1 over the removal rate. So let me finish with some generic examples, because it's not just the death rate. It's whatever the removal rate is in the equation. So for example, let's say the equation that denotes the infected rate in some model. It has some positive terms somewhere here, and then let's say it has a natural death rate, and then it has, let's say, recovery rate from the disease. So that's the recovery rate. So notice that if I rewrite this equation, again, forget about the possible extra terms. Let's say all the negative terms are here, mu I, ri, right? If I actually combine them, I can't say this is basically the death rate, because it's a combination of the death rate and the recovery rate. So that's why you will hear often in math biology papers the notion of the removal rate from an equation, because it's a combination of maybe different factors. It can be more than 2 or 3, right? You could have the disease mortality and so on and so forth. So you could have lots of negative terms in the form of a rate, in which, if you combine them, you get what we call a removal rate. But the interpretation is the same, except that when I take 1 over mu plus r, you don't call it lifetime expectancy, because it takes into account more than just natural death rate, so more than just the natural life expectancy. It takes into account also the reason of living I because of the recovery. So there are basically 2 ways to leave the infected class: natural death, recovery rate. So this will be basically the expected time spent in the infected class. So this has to do, of course, with the duration of the disease and your chance of dying from natural causes if the disease, for example, doesn't kill you. If it kills you, there should be another term here that indicates the disease mortality. So as a quick example, let's say the natural mortality is 0.012, and then let's say the recovery is 0.3, and you can check this with your own calculator. 1 over mu, just 1 over mu, that will be the life expectancy, irrespective of the disease. Right? So, regardless of the disease, 1 over mu, 83.3, that's going to be the life expectancy. The removal rate, the reciprocal of the removal rate, if I have 1 over 0.012 plus 0.3, If you do it with the calculator, this should be 3.2, much lower. So this is basically the time spent infected. So a completely different interpretation, although life expectancy plays a role, obviously, because it's part of the removal rate. And obviously, you'd expect it to be much shorter than the life expectancy overall. And depends on the unit measures, of course. I mean, if these are years, this will be pretty long disease. So this is probably not realistic, right? I mean, it should be much, much bigger than 0.3 for short-lived diseases. The meaning, I mean, how realistic these numbers are, of course, has to do with the time unit built in the model. Are we talking about days, years, and so on and so forth? So I will go back to these discussions, but at the very least, from this first part of the lecture or the course, always remember that the main reason for putting these removal rates in the denominator is because of this interpretation of the reciprocal of the removal rate. So I think that's it for today.